Bernoulli's principle says for a fluid traveling parallel to a surface that fast-moving fluids exert low pressure and slow-moving fluids exert high pressure. It's important to realize that with Bernoulli's principle, we're not talking about movement of fluids perpendicular to a surface. We're talking about movement of fluids parallel to a surface. And fluids that move parallel to a surface, fast-moving fluids exert a low pressure on that surface. Slower-moving fluids, moving parallel to the surface, exert a higher pressure. You can see that if this is a surface, this higher pressure would overcome this lower pressure, and you would have a net force, as shown here by this blue arrow. So, a reminder that Bernoulli applies when a fluid moves across, not against, a surface. Let's go through a couple of examples. This is essentially the cross-section of an airplane wing, or also a helicopter propeller. It's a shape, it's basically called an airfoil, and that airplane wing is traveling as we've drawn it to the right, which means that the air particles that this wing bumps into on the front edge have a choice. They can either go above the wing or below it. Well, because of the shape of the airfoil, the air particles that go above the wing have to travel a little bit faster than the air particles below the wing. These air particles this one goes a longer distance in the same amount of time that this one goes a shorter distance. So up above the wing we have fast-moving fluid, and on the bottom portion of the wing we have a slow-moving fluid. Fast-moving fluids, according to Bernoulli, exert low pressure, and slower-moving fluids exert a higher pressure. Pressure is always going to end up with a push from Pressure is always going to end up with a push from high to low pressure, which means we're going to get a net force upward due to Bernoulli. Now, of course, on an airplane, you've also got a downward force due to gravity, and the ratio of these forces allows a plane to go up and down and fly at a constant altitude when needed. Now, there are other aspects that help with the physics of airplane wings and helicopter propellers. We're just talking about the Bernoulli aspect. A frisbee works the same way. When we throw a frisbee through the air particles on the top have to go a little bit faster because they have farther to go. Fast-moving fluids exert low pressure. On the bottom, slower-moving fluids exert a higher pressure, so there's a net upward force which helps keep the frisbee in the air longer. What about windows and high winds, like in tornadoes? When there's a high wind, the air velocity outside the building is very high. The air velocity inside the building is comparatively less. So a fast-moving fluid exerts low pressure, a slower-moving fluid exerts a higher pressure, and windows tend to burst outwards. You might have had this experience if you're driving down the interstate with the window down. Little wrappers and small pieces of paper always tend to blow out the window, never in. How about in a windstorm? We've got wind, all of these fluid particles traveling parallel to the roof. Inside, there is a net lower velocity. Fast-moving fluids exert lower pressure. Slower-moving fluids exert higher pressure. This is going to tend to lift the roof up. And because the surface area on a roof is quite large, the pressure difference doesn't have to be very much to have big effects. That roof lifts up a little bit, then the wind can catch underneath it and possibly rip it off. And what I have here is a photo of a freely rotating plastic spoon caught in a water stream. The large number of water particles on the right, all moving in the same direction, give a high velocity, and by Bernoulli a low pressure on that side, The gas molecules on the left, while each moving faster than the falling water molecules, are moving in random directions, giving a net low velocity and hence higher pressure on the left. Thus, the spoon leans and stays leaning into the water stream. So on the left side here, we have low velocity and higher pressure. So there's a push to the right. Let's summarize. Bernoulli's principle states that, parallel to a surface, a fast-moving fluid exerts lower pressure than a slow-moving fluid. We demonstrated Bernoulli's principle in the real world through various examples. There are two methods for rationalizing Bernoulli's principle, and that will be the subject of our next lesson. And as a reminder, you can see on the right here, with Bernoulli's principle, we aren't talking about fluids exerting forces perpendicular to surfaces, like the wind blowing in these sails. That's not what we're talking about with Bernoulli.